Ladies and gentlemen, good morning. Recording has started, so we are ready to go here. Just so everybody knows and nobody says anything stupid or inappropriate or both. So. First, as far as the calendar goes, this morning I updated a couple things on the calendar. Last week on Friday, you took the quiz. The quiz is graded. It's back in the tray back there, so hopefully you got that by now. Second, the lab that we did not yesterday, but 2 weeks ago with the carts that were on the table and rolling off there. We have enough information now to answer those questions. We have enough information to make those graphs, so please get that turned in ASAP. Okay. As far as the rest of the calendar goes, today, after we review some of the stuff that we did yesterday, we are going to introduce Newton's third law. It's the only one of Newton's three laws we haven't talked about yet. It's a one-day kind of thing, so we'll talk about that today. Then, on the calendar, I have Magic School Bus video on Monday, test on Tuesday. But I'm realizing now that we probably should spend Monday doing some applications of Newton's third law, how it fits together with Newton's second law. So I'm thinking I'm probably going to push test back to block day, or the first part of block day. Not all of block day, but the first part of block day. So I'll probably push test back to Thursday of next week for you guys, Wednesday for the other class. Okay? Good there? I'll fix it sometime.
Good there.
Yeah. Thank you. Thank you. All right. Yesterday, we took data for the Newton's second law scooter lab. This is what it looked like, right? And at the end of class yesterday, we collectively filled in these charts with the distances that these people traveled and the time that it took these people to do it. Last year, I saved the data. And so this is my data from last year. Apparently Yasmin was my skater with constant mass. Okay? And then in this data table, 3 different masses. Okay? So this is the data that I'm going to show you. It's obviously not going to match your data from yesterday, but you'll get an idea. Okay? So as far as the graphs go, I told you yesterday in class that you had to make for me 2 graphs. On each of those graphs, there will be 3 lines. So in the data analysis section, I believe that most of you used the kinematic equation to calculate the acceleration. Then use the calculated acceleration and using Newton's second law to figure out the frictional force. I think most of you got through that part. Let's talk about the graphs. Okay? First, time squared versus position. For each person that was skating, you have distance values and time values, right? You've got these distance values here, you've got these time values. For each person that was skating, you have 4 distances and 4 times. But you're not going to make a graph out of these distances and times. You're going to make a graph out of distance or position and time squared. So either you have to set up Excel to do this, or you have to manually calculate what all of these values squared is. Does that make sense? So in Excel, it would look something like this. You're going to have 3 separate data tables. Distance and time, and then I set up Excel to automatically calculate the squared value of all those. You can just have 2 columns, one for time squared and one for distance. If you know how to use formulas in Excel, fine. If you don't, you can just do it on your calculator. Okay? But you're going to need time squared and distance. Okay? Good there, to start. 3 separate data tables, one for each child. That means if you're on the first data table, that would be Kevin at 1 force, Kevin at the second force, and Kevin at the third force. Each one of those childs gets its own data table. Or if you're on the back side, it's each person gets their own data table. Good there? Okay. So first thing you're going to do, you're going to highlight, maybe not. I'll go over here. So the first thing you're going to do, you're going to highlight the squares, or not. soon as my computer decides it's going to cooperate. Stand by. Stand by. Sweet. Awesome. Okay, let's do this. Okay, so there's my values again. It doesn't like appear like doesn't want to do this. Maybe this will work. I'm stumped. I'm clicking and nothing is happening. Yeah, technology is great. Yeah, pound it. That'll help. So this is gonna be great when the next class watches it. It's gonna be. Yeah, I'm sure this is gonna be great for them. So.
Can I just say follow me on Twitter at KDEN7?
You can. You might sound lame doing so, but you can.
Burn.
All right. So just my mouse is not working. Awesome.
Maybe like a ball. It's like flickering.
I know, but like it won't let me click. It lets me right click, but not left click. It is. I'm recording all of this. So.
No. Wait.
Plug it in, unplug it.
No, it's not explain. It's right clicking.
Throw it up the plane. You want to go over the desk?
No. Try this. It does it here. Why? I don't understand. It right clicks here, but not on that here. Let's see if this works. All right. Okay. Sorry, everybody. I have no idea what was going on there, but now I'm back. Okay. So once you've got in your time squared values and your distance values, you're going to highlight just those 8 squares for the first data table. Don't try and highlight all of your numbers at the same time. That won't give you separate lines for each graph. First, you have to make the first data table. So make sure that time squared is in your first column, because then it will automatically show up on the x-axis. So highlight these 8 squares, go to Insert, go to Scatter, and then pick this one that just has the dots. And there's your first graph. Okay? Good there? I think all of you got that part. Here's what you need to do next. Once you've made your graph, and this doesn't have axis labels on it yet, it doesn't have a title, it doesn't have trend lines, any of that stuff, okay? But once your graph is made, if you right-click anywhere on it, or you can also go up this green bar up at the top that says Chart Tools. On the Design tab, there is a link here that says Select Data, or if you right-click, there's also Select Data as well. When you do that, this window will pop up. Okay? It says Add, Edit, Remove. This is where you control what data is going to show up on your graph. So right now there is one set of data on the graph. Excel has called it Series 1 because you didn't give it any other information than that. So I'm going to click on Series 1 and I'm going to click Edit. And when I do, this window pops up. Now, it's got these squares in here that tell me what I'm actually graphing, but up at the top square it says series name. So here's where we can distinguish one graph from another. So I believe, if I remember correctly, this data was from the person with the same mass who we used at different values. So let's say we'll call this one Kevin, and then what was the first force value that we gave for Kevin? Does anybody have it written down real quick? Flip on the other side. 27.83. So we can go 27.83 newtons and call that the name of this. If I hit OK, over here on the side it says Kevin, 27.83 newtons. Okay, is that good there? Now, here's the important part. Next, where I clicked edit, just to the left of it, it says add. I'm going to add another set of data to this chart. So I'm going to click add, and this same window is going to pop back up. Okay? So as far as the name goes, I'm going to call this one Kevin, but I'm going to call the next force value, what was the next force value up for Kevin? 39.26. So I'm going to call that the name of this. Now, in these two squares where it says series x values and series y values, this is where I'm going to tell Excel what I want to graph. So I'm just going to move this over here. The x values for this new set of data are these time squared values. The time squared values that are in the second set or data table that you plugged in. Does that make sense so far? So all I'm going to do is I'm going to click in this box where it says series x values, and then I'm going to highlight these four. Just those four, because when you're doing it this way, you tell the x values and the y values separately. Then when you come down to the next box, it says series y values. First thing I'm going to do is I'm going to delete everything that's in there, because if you don't, it kind of messes everything up. Then I'm going to go and highlight these four distance values, because that's what I want to be on my y-axis. And if you look down at the graph, right, it added another set of boxes, right? These are the red squares. Does that make sense? Okay. So then I'm going to hit OK, because I'm done with this set of data. So now I've got two lines on the same graph. One at Kevin 27.83, one at Kevin 39.26. But I'm not done yet. I'm going to add another set of data. This one I'm going to call Kevin, and I think it was like 50 something, right? 47.26. So I'm going to put that in there, 47.26 newtons. In the box that says series x values, I'm going to my third data table. These are the numbers that I want on the x-axis of that third line. I'm going to go in here, get rid of this, and on the y-axis, I still want the distance values. So you'll notice that automatically, that third line has come up now. Does that make sense? Okay. So I'm going to hit OK. I've gotten my three sets of data, so I'm going to hit OK here, and that takes me back to my graph. Okay. Now, I can go in, and I can click each of these set of dots separately, and so I can go up, and I can add their own trend lines, right? I want a linear trend line. But if I display the equation on chart, right, that little box down there, that will give me information about this trend line, like its slope, which is kind of important. Okay? And I can do that separately for each of the three graphs. Linear, display equation on chart, now it gets its own equation and its own line. And I'll move that over just so it's a little easier to see. And then the green ones, I can do the same thing. Just like that. And now you've got one graph that has three separate lines on it. Good there? That's how you make a graph with separate lines on it. It's the Select Data tab. Okay? So this one, this is one of my graphs. And now we have to add like title and axis titles and all that good stuff. Okay? But that's one of my graphs. The second graph is going to be for the data table where we did the 3 individual skaters. And each line will be a different skater. Okay? Is that good? So that is how you are going to do numbers 3, numbers 4, and number 5 in the data analysis section. Okay. Sammy, go ahead.
Do you want us to put this up in the
No, that's okay, because the intention of that data table was that we were pulling them all with a similar amount of force. So you could, if you want to, in the name, like, are you saying like in the naming of the graph? You could if you want to, although in that case, the intention was I tried to do them with a similar amount of force. But if you want to throw it in there, feel free to do so. Okay? It was more, Sammy, it was more important on that graph because it was Kevin at 3 different forces. That's why, that was the way I was distinguishing one line from the next. Okay? All right, good there? All right. With that being said, let's move on to Newton's third law, action-reaction. So we've already talked about Newton's first law. Newton's first law gets summarized in one word, right? What is that one word? Inertia summarizes Newton's first law. Newton's second law talks about acceleration and how much acceleration an object has, and that gets summarized by our equation sigma f equals m times a. Okay? The third part, Newton's third law, doesn't necessarily talk about acceleration or something staying still. It talks more about interaction, or what happens when 2 objects come together. Okay? And we summarize that with action-reaction. Okay? So my little subtitle says, blue girl, stop pushing me. Striped girl, no, you stop pushing me. It's going to be hilarious in like 5 minutes. Right? Promise. Yeah. No, striped girl.
Stripped.
All right. So, Newton's third law. Newton's third law is written as such. When one force exerts a force on a second object, the second object exerts a force on the first that is equal in magnitude but opposite in direction. That's how we write it in words. Most of you have probably heard it a different way. Okay? Most of you have probably heard it in the form of, for every action, there is an equal and opposite reaction. But, to me, that doesn't make a whole lot of sense. This says, if I push on an object, if I exert a force on that object automatically exerts a force back on me that is the same amount of force, but in the opposite direction. Does that make sense? Forces always come in pairs. You can't have just a single force out there in the universe. Now, we might only be concerned with one of those forces, like if we're talking about an applied force or something like that, but there is a match to that force somewhere out there in nature. And it's exactly as big, but in the opposite direction. Okay? Good there? So, are we done writing? As far as that goes, okay, we call these equal and opposite forces action-reaction forces, or action-reaction pairs, depending on what book you read. Okay? The important thing is that these objects are equal in magnitude and they are opposite in direction. If you've been paying attention for a while, right, this might start setting off alarms in your head. If we have 2 forces that are equal in magnitude but opposite in direction, that sounds a lot like another concept that we've already talked about, yes? net force, more specifically, if they're equal in magnitude but opposite in direction, that's equilibrium, right? And equilibrium says that an object is either at rest or moving with a constant velocity. So if that's the case, right, what would that mean? Things would never accelerate. If this is true, okay? So is it true, or do we just throw it in the group because, you know, the first two of Newton's laws were pretty good, so, you know, even though we missed on this one, you know, we'll keep it in there, okay? No, it's not true. There's a reason how we have to interpret it, though. For example, striped girl, blue girl, there they are, okay? So, striped girl pushes on blue girl. There it is, okay? Automatically, without having to try, right? Blue girl is facing the other direction. But Newton's third law says that if striped girl pushes on blue girl, what automatically has to happen? Blue girl pushes back on striped girl. Okay? Same magnitude, different direction. Like that. Okay? Does that make sense? Okay. Do those two forces cancel each other out? No. Right? Why don't they cancel each other out? They're not in the same direction, they're in opposite directions, right?
Different objects.
But they're on different objects, right? Two forces that are the same on the same object will cancel each other out, right? This cup sits on the book. There's a force of gravity pulling down on it. There is a force of the book pushing up on it. Those two forces are on the same object. They cancel each other out. But this force is on blue girl, and this force is on striped girl. Will they cancel each other out? They can't. They're not on the same object. If we drew a free body diagram, would those two forces appear on the same free body diagram? No. One of them would be on blue girl's free body diagram. The other one would be on striped girl's free body diagram. Those forces can't cancel each other out. Does that make sense? Okay.
But isn't blue girl pushing back on striped girl also?
Yes.
So wouldn't that force cancel out? No.
Because one of those forces, striped girl pushing on blue girl, is a force on blue girl. Does that make sense?
Yeah.
But blue girl pushing on striped girl is a force on striped girl.
Oh.
Those two forces can't cancel because they're not on the same object. So in this case here, right, well protected, safety first, right? Okay. In this case, what would start happening as striped girl pushes on blue girl? Come on.
There's striped girl and move backwards.
What else would happen though?
And blue girl move forward.
Right. They both start moving, but they move in opposite directions, right? If they're really good rollerblades, yes. Okay. Or ice skates or something like that. Okay. Now, will they necessarily move at the same rate? No, because the acceleration of each object depends on force, but it also depends on what? Mass. They're feeling the same force, but are they the same mass? We don't really know for sure. Okay? Does that make sense? All right, another application. Now, go ahead. Come on.
If the two girls were like weighed the same, would they both go the same distance, or?
Same distance is kind of tricky. Okay? Because what would cause them to slow down and then stop eventually? Friction. So if they both experience the same friction, then yeah, they would, right? But let's say, like, you know, one girl is standing on the edge of an ice skating rink and the other girl is standing on the floor outside the ice skating rink. One girl pushes on the other girl. The girl that's on the ice skating rink, she would start moving backwards, yes? Okay? But would the other girl start moving forward? No. Or just like this, right? If I push on the wall, I kind of go backwards, but does the wall go anywhere? No. Or at least least it doesn't appear that it goes anywhere. Okay? Because how much objects move depend on the forces and the mass of that object. Right? So let's take this example. Let me draw this so that the other people in the other class know what we're talking about. Okay, so there's the floor, but this part of the floor is an ice skating rink. That part isn't. So here's our own version of Blue Girl, okay? And there's our own version of Striped Girl, okay? So Blue Girl pushes on Striped Girl. So there's a force that way. We know that Newton's third law says automatically Striped Girl has to push back on Blue Girl same force, different direction. But as we've already established, what's going to happen to Blue Girl now? She's going to start moving backwards like this. But is Striped Girl necessarily going to go anywhere? No. Is that because she didn't feel this force that Blue Girl originally applied to her? No. But is that the only force that she's feeling? No. What's going on down here by Striped Girl's feet? She's got friction, right? So even though Blue Girl applied a force to Striped Girl, that's not the only force on Striped Girl. So the static friction between Striped Girl's feet and Blue Girl's force cancel each other out, and Striped Girl doesn't go anywhere. But because Blue Girl doesn't experience that friction, or that much friction, even though they experience the same forces from each other, their net force is not the same. Does that make sense?
If they were both on the ice, would they both go the same amount of distance?
That depends on what other thing, right? So let's say now, let's say now, ice skating rink now extends the whole way. Okay. Blue Girl, Striped Girl, force, okay? Judging by my picture here, what would we say about the masses of these two objects?
Striped Girl weighs a lot.
Striped Girl has a lot more mass than Blue Girl does. So that means they experience the same force. But would they start moving the same then? No. Which one's going to move faster in this interaction? Blue Girl. Lower mass, greater acceleration. So which one would end up traveling farther? Blue Girl. Even though they experience the same frictional force, maybe not exactly the same because of coefficient of friction and stuff like that, but Blue Girl, because she started with a greater acceleration, attained a greater initial velocity, so she travels farther. Does that make sense?
But if they were the same.
If they were the same, then yeah, it would all be symmetrical. Good there? So, here is a famous application of this situation that shows up somehow, some way in pretty much every physics book I've ever read before, okay? And it's on the front. So, it's the horse and the cart, okay? Pay no mind that there's a horse that's talking in this cartoon, okay? It just happens to be part of it. So, the farmer says to the horse, hey, giddy up, pull this cart so we can get going. And the horse says, no can do, my friend. It's not exactly what he says, but it's the gist of it. He said, for me to pull this cart would be a futile effort. Are we give him a futile effort?
Yeah.
It's just not worth it, right? So the horse reasons, hey, if I pull the cart pulls back on me. And by Newton's third law, it's a horse that knows physics, right? Okay. Newton's third law says these forces are equal and opposite, and they'll cancel. That means a zero net force won't get us going anywhere, so I might as well not even try. But we've already established, is the horse right in this situation? No. If we take a look at the horse and the cart separately, right? Horse pulls on cart, so cart feels a force. This one's hard because there's force and horse in the same, yeah. So, horse pulls on cart. No, I'm going to screw up somewhere along the way, just in warning you guys. So. Horse pulls on cart. Cart feels a force, but we know that Newton's says this has to happen, yes? If there were no other forces in this situation, what would start happening? If those were the only two forces in this situation,
Well, it depends on the mass.
well, it would depend on the mass, but generally, what would happen here?
Nothing. Well, like in real, like
If these were the only two forces, what would the cart start doing?
it would accelerate at a constant rate.
In which direction? What would the cart start doing?
Forward.
How many forces does this cart have on it?
One.
One. It's to the right. So it would start doing what?
Oh, they would hit each
It
other.
would start accelerating to the right. But the horse, how many forces does the horse have on it?
One. They would go like this.
One. It would start accelerating in this direction. What would happen? They'd run into each other in the middle. Maybe not exactly in the middle. That would depend on the masses. If you guys had a tug of war on a completely frictionless surface,
That'd be really hard.
it'd be really hard because as soon as you pulled on the rope and the other people pulled on the rope, what would start happening?
They'll fall.
Well, yes, okay. But you'd both start moving towards the middle because there's no other forces there. Newton's third law says equal and opposite. If I pull on you, you pull on me. How hard? Exactly the same amount, but in the opposite direction. So can this be the only thing going on here?
No.
No. What do we know happens to the horse?
He's pushing on the ground. Oh,
Well,
he's forward.
He moves forward. So to get that horse to move forward, there has to be a force in this direction. It has to be bigger than the blue force. So now there is a net force moving in the other direction. Right? How does the horse accomplish this?
He pushes on the ground.
Okay? There's another object involved here. It's the world, not drawn to scale. But if the horse pushes on the ground, what does the ground do? It pushes back. How hard? Same. Not harder, the same. As long as he pushes on the ground harder than he's pulling on the cart, net force forward, what starts happening to the horse now?
It says this.
That horse starts accelerating. But that leaves one question unanswered.
Where's the word go?
If you look at this picture, how many forces are acting on the Earth? One. Is it balanced out by anything? No. So what's the Earth going to start doing here?
Moving that way.
Moving the other way. Ready? Feel it.
Whoa.
Just move the Earth. Did you feel it?
And now.
That's good.
You won't be.
The force. I did wake Jamie up. I apologize. So, actually, I've never really apologized, but you know. So, unbalanced force acting on the Earth would cause the Earth to accelerate. Does the Earth move? Yeah. Is it any perceptible amount? No. But that raises the next question. What's the next question? I know somebody's got it. No. There's a question that's out there floating around. Somebody's got
Why
it.
doesn't the Earth move?
Well, we just established why the Earth doesn't move. It really does, but what? It just has a really big mass, so its acceleration is small. Somebody's got the next question. I know it. Somebody always comes up with the next question.
Something to the cart.
No, not with the carbon.
What's
It's with the Earth.
What does the farmer say to the horse?
Ah, there it is.
Yeah.
So, what happens if everybody jumps at the same time?
Doesn't matter because
At this point, if we all jumped, if we just said 1, 2, 3, jump, would anything happen?
no, that's just right.
No, because I'm over here and some guy in China is over on the other side and he's pushing the same way. So that leads to the next question,
What if
which
we're all
is,
on one side
what
of the
if we all go to Australia? And we say, everybody, 1, 2, 3. So, and the answer is, I've never calculated it before, so I don't know.
Can you
Wait,
calculate?
that'd be so
Be alive. No, I don't think so, because I think when you do the math, you realize that it really would make a
But
difference.
there would be one person like on the other side of the world that would be like,
Yeah, I mean, maybe Monday will work. How's that?
They just
All right, so
there's no way it would be possible to happen.
we've already established the facts. Here, let me wrap this up real quick. Okay? We've already established the fact that action-reaction forces will not cancel each other because they act on different objects. We will look at applications of this both conceptually and in problem form on Monday. We'll watch the video on Tuesday, test on Wednesday. Got it?
Got it.
Have a good weekend,
We're gonna
everybody.
have to save the road for
And
Monday.
then,
We're gonna have to like go to one side.
Do you have a lock next week?
Everybody jump!